Hey, welcome back. This time we're looking at heat transfer and calorimetry once again. In the last video, we talked about what is heat transfer, and you know that as things getting hotter and all around us, we're transferring energy from one thing to another, and the flow of energy into molecules we call heat. And so whenever two objects come in contact with each other, if one of them is hotter, the heat will flow between them until they have the equal temperature between them. And so we call that thermal equilibrium. So we're going to talk a little bit more about thermal equilibrium and how we use that to figure things out. And that's what calorimetry is. So let's kind of go back to our equations to sort of review here. And we had this equation right here where we said Q, which is the heat transfer, or just heat, equals the mass times the specific heat times the change in temperature. And we talked about how specific heat is specific per material. So every single material has a certain amount of joules of energy it takes to raise a certain amount of it per degree, or in this case it says Kelvin, so per Kelvin. But you could also have that be per degree Celsius, because Celsius and Kelvin are the same amount of increment per degree, right? So specific heat per material is going to change, right? So if I'm heating up aluminum, look at this, it only is going to take me 897 joules, but to heat up the same amount of water, it takes me 4,184 joules of energy. So that's why if you stick some aluminum in a fire, it's going to feel hot real quick, but if you stick some water on the fire, it's going to take a long time. It's just this specific heat bit. So that's what the C is here. And of course, we have to have our change in temperature and we have to have our mass for this to make sense, because this tells us how much energy per mass and change in temperature. So there you go, boom. That's going to give us our Q. We also talked about how power equals energy over time, right? And Q is energy. So you could also say that power equals Q over time, right? Or you could say that power times time equals mass times specific heat times change in temperature. So this might come in handy. But another thing we're going to look at is the idea of calorimetry. Now let me throw a picture up here for you to take a look at. So this is a pretty typical calorimeter. And so what does a calorimeter do? So a calorimeter works off this idea of thermal equilibrium, where what we're going to do is we're going to have something heated up right here. And we're going to stick that underwater in a sealed container, so it's as much of an isolated, closed system as possible. And so what's going to happen? Well, this is the hotter object and this is the colder object. So the way that this works, the rule is that the heat will always flow from the hot to the cold until they're equal. And so the idea is the amount of thermal energy that is in here will transfer to the water. Okay? So basically, my equation is going to look like this. My change in energy, so as I look at the water, my change in energy is going to equal my Q, which equals mass times specific heat times change in temperature. And so what we observe in a closed, isolated system like this is that the mass of this, let's call this the mass of A, right, times the specific heat of A times the change in temperature, right, of this whole system. So we're going to look at the change in temperature of the whole system here. Sorry, not equals. Plus the mass of B times the specific heat of B, and so that would, in this case, be the water, times the change in temperature of B. So actually this would be change in temperature of A, and then plus change equals 0. Okay? So they're going to cancel each other out. So basically, what this equation is saying is that the Q of this, the heat in here, is going to transfer into here, and whatever this goes up is the same amount that left here, and that should make sense. And so if you were to calculate what is here and what came out of here, it's going to equal 0 overall. All right. So what I'm going to do for you is we'll do a little problem real quick on this idea and see if we can make this work. All right. So here's the information we have. So say you have a car. Say it's got a solid cast iron engine block, and that engine block has a mass of 2.50 times 10 to the second kilograms, or 250 kilograms. Okay, and say that the temperature of the engine is about 35 degrees Celsius. So it's not quite warmed up yet. But let's say for one reason or another, a hose comes off, all your water leaks out onto the ground. See, I've cleverly drawn all that. And then this is not a good thing because the air is only 10 degrees Celsius. So the air is a pretty chilly, not quite freezing, but getting close. And so we want to heat up our car. It's cold. And so let's say that we know that the actual amount of heat that ends up getting transferred from the water in the engine to the air is 4.40 times 10 to the 6 joules. So here's the question then. Could we figure out how much water came out from this information so that we could refill our car with the amount of water? Well, it turns out we can. So I'm going to go ahead and just throw this up here for you. So we know that Q is going to equal the change in energy. And so Q is going to equal then the mass of the water times the specific heat of the water times the change in temperature of the water plus the mass of the block, the engine block, because that's what was hot, times the specific heat of the block times the change in temperature of the block. So in this case, the total change in temperature is where the engine goes to become the temperature of the air. All right. So how much water is lost? So so we need to figure this out because the water is part of this thing. We need to put it back in. So if we go ahead and plug in what we know that our Q right here is, sorry about that. We know that our Q is the amount of heat transferred. So that's 4.40 joules, or 4.40 times 10 to the 6 joules. Our mass of water is our unknown, but we know our specific heat of water, and we know the change in temperature is 25 degrees. Right? We know that the mass of the iron, the cast iron, so the engine block is made out of cast iron. So the mass of the iron is 250 kilograms, and we know that the specific heat of iron is 450. We can just look that up. And we know that the iron is going to change temperature 25 degrees. Right? So for a total heat loss of 4.40 times 10 to the 6 joules, we're going to just go ahead and plug this stuff in. So we'll multiply this and we'll subtract that over here. We've got that times that. We're going to divide by that. We find the mass of water is 15.2 kilograms. So this is kind of one of the ways that you can do it. In the calorimetry sort of situation, you could look at this transferring into this. So you'll know that this equals this, or one of them is going to be negative. This one's losing, and this one's positive, and so they'll add up to 0. So that's one way that you can do it. But basically, you understand that a change in energy in an isolated closed system is always going to equal 0. Or you could look at a situation like this, and you could realize that that the Q is going to equal the change in energy. So I had a change in energy. I had a heat loss right here of 4.40 times 10 to the 6th. If I know that, and I know my temperature change, and I know my mass, I could figure out the mass of water that was also in there. All right, so that's a quick little problem, and hopefully that helps for you guys to understand some of how we use this to solve different things we have going on.